My name is Zach Harabedian. I'm a principal product architect with NetApp. Thank you for coming to our session today. We're going to be going through scaling Gen AI, talking about some of the operational challenges with running Gen AI workloads on Kubernetes. And with that, let's get into the agenda. So first, we're going to just talk a little bit about the general infrastructure landscape, talking about some of the challenges that exist today. Then we're going to go through AI inference. How is that different from training? We're going to talk a little bit about why companies are using Kubernetes for AI inference. What are the benefits there? But also, what are some of the challenges? What are the options out there to optimize your workloads on Kubernetes? How can we leverage those different strategies to tackle your compute costs, your storage challenges? And then we'll talk a little bit about some of the solutions that NetApp is offering, as well as how we tell a better together story with the solutions on AWS. And then shortly after that, we'll wrap things up. All right, so when we talk about infrastructure and AI, I think we're no longer at those early stages in the AI hype. We're in that time slot where people are using AI applications for their day-to-day workflow. We're pretty dependent on some of these AI applications, and we're starting to see some of them in production. So it's no longer like that project phase. So what I'm showing here is what is that impact of if you didn't have those GPU resources available to power those applications, what would the impact be to your business? So I think you can see here is pretty self-explanatory that we're really dependent on those GPU resources, and they're becoming more and more a critical piece of our infrastructure. And furthermore, that's not only making us think about how do we make sure that we always have those GPU resources available, but how do we make sure that we're running things efficiently? How do I decide, should I run this on-prem? Should I run this on AWS? Things like that. So what we're showing here is, how do the cloud egress charges impact some of your decisions? I think it's pretty common that we can assume that our Gen AI workloads and these GPU processors are going to also be dependent on a lot of data coming in and out. So what we're showing here is how does that affect the cost of our cloud storage? Should I be moving things around? Should I go back to on-prem? All these decisions are something that is probably going to come up as you are trying to figure out how to host your workloads. So let's talk a little bit about AI inference. What exactly is that? AI inference is something that happens after your model's already been trained, and it's a way to introduce new data to your existing model. There's also opportunities to be leveraging your chatbot applications that would be considered like an inference, right, where you're interacting with your already trained model. So really anything that comes after that model's already been trained is what inference is going to be used for. And if you think about, why is that important? Well, if you want your model to stay relevant or your applications to be relevant, things change all the time. You need to be able to introduce that new data to your model to make sure that you're still serving accurate and reliable data that all of your teams depend on. So that also comes with the need for GPU resources to make sure that you can reliably run your inference workloads. It's a critical aspect, and there's also a critical aspect of where does storage come into the equation, right? When we think about your interactions with like a chatbot, you want to ask your question and you want an immediate response. So you need to make sure that you're using efficient storage solutions to make sure that your inference jobs are running quickly and you're getting the data in and out quickly for your users. Okay, so let's talk about the role of Kubernetes in AI inference. Why are we not choosing just to run things on bare metal? Well, Kubernetes does a lot of neat things that, out of the box makes it a good tool to leverage your AI workloads on. We'll start with the scalability aspect. Well, the concept of microservices is making things portable, right? Being able to shift things between, multiple clusters, multiple clouds, whatever the case might be. It makes it easy to pick up your Docker containers, run them wherever you want. So there's that flexibility aspect to it. And there's, out-of-the-box support for maximizing your resource utilization, right? So when we think about like the Kubernetes scheduler, out of the box, its job is to understand all of those requirements of your applications and your containers and make sure that you are, respecting all of those requirements, taking a look at your footprint of what's running in the cluster, and adequately scheduling them as the requirements dictate. So in terms of deployment, there's also a lot of neat things that you can do with Kubernetes because it's all a declarative management through like YAML files. So you can define your YAML files. If you have a new change, a new image that you want to introduce to your model, you just change your YAML file. Out of the box, Kubernetes can do some, a rolling update to make sure that new version safely gets applied throughout your cluster. All right, so now, how do we operationalize, scaling our models? What are the different components of Kubernetes that really makes all of this possible? Well, one of the first decisions you're going to need to figure out is your horizontal pod autoscaler, or your HPA. So what the horizontal pod autoscaler is responsible for doing is saying, okay, let me define how I'm going to add more replicas or remove replicas of an existing deployment. And you can define things like if my CPU utilization of a given pod goes above X, add these replicas, or define like a target utilization. So you define any custom scaling policy that you want, and the horizontal pod autoscaler's job is to add or remove those pods. So that's really the first layer. And then once you have figured out how you're horizontally going to manage your pods, you need to figure out, okay, how do I vertically size my pods? So this is taking the idea of your resource requests. So in Kubernetes, you're going to define, I want X amount of memory, I want X amount of CPU, and I need X amount of GPUs. Well, if at the end of the day, if you're a data scientist, application developer, you want your application to run, right? Like, you don't want someone waking you up at 2 in the morning saying, hey, your application's down, it has an out-of-memory issue, we have to figure this out. So things tend to get a little bit over-provisioned, and that's what the vertical pod autoscaler can do. So it can understand, okay, we see you're requesting X amount of resources, but maybe you can change that to Y, and by doing so, the byproduct might be cost reduction, right? So pretty neat tool out of the box that you can make sure your resources are adequately sized. Last but not least is, we talked about horizontal scaling, vertical scaling, but what about your infrastructure? Like, what about the number of nodes running in your cluster? That's what the cluster autoscaler can help you with. So what the cluster autoscaler is responsible for doing is taking a look at pods coming into your cluster. If pods are in a pending state, the cluster autoscaler can say, oh, hey, there's something for me to do. I need to add X amount of nodes in this node group and make sure your infrastructure gets spun up. And then the Kubernetes scheduler can make sure your pods are landing on those nodes. So when you think about all the different components that can work together, these are all like pretty critical aspects of managing your Kubernetes cluster. And all of this is really not specific to AI in any sense, but it's important as we go through the rest of our talk today. Okay, so now when we talk about Kubernetes specifically and the challenges for AI inference, there's a few things that are going to always come up. So the first is around resource management. So in Kubernetes, you define your pod spec, right? And your pod spec is going to say, I need X amount of memory, I need X amount of CPU. And what you can do with that is you can say, give me a fraction of that. So if my node has, 24 CPUs, maybe my pod only needs 8, right? So you can just define in your pod spec essentially a fraction of what that node has to offer. The Kubernetes scheduler understands it. The cluster autoscaler understands it. Everything is great. But with GPUs, it's not the case. Kubernetes doesn't understand natively out of the box what exactly is a fraction of a GPU. There's a few more things that you need to think about if you want to get into that arena. But that's really the first challenge. So when you think about all those different workloads that are going to be running, all those inference workloads that are going to be running, you need to understand, am I actually using a full GPU? Or is the actual utilization maybe half of a GPU, just as an example? So it's another thing that you'll need dedicated monitoring tools to look at and understand. And then the scalability aspect comes into play. So you've probably read plenty of articles out there about how scarce GPU resources are, how companies are on a backlog of some sort to get more GPUs into their environments. And the same thing happens in the public cloud, right? Everything is truly supply and demand. So there might be times where you're requesting a GPU instance and there's none available in that specific availability zone. So you need to make sure that you're designing your applications to be resilient and make sure that you can run across multiple AZs or you have that flexibility. In terms of cost, I think GPU instances are among some of the most costly instances that you can be running. And more often than not, they're probably bursty, especially for inference workloads. So your typical approach might be, okay, maybe I'll buy a reserved instance or a savings plan. Well, that might work for a lot of your infrastructure, but if you're bursting up and down, you might be wasting money with those types of commitments. So just another thing to think about. And then last but not least, the operational complexity requires a deep understanding of all those different components we talked about in the previous slide, making sure that you're scaling horizontally, you're vertically sized correctly, and you're scaling your infrastructure appropriately. So a lot of different considerations that you need to tackle, all on the compute side. But the compute side also has another set of challenges in terms of storage, right? So you have your storage challenges in Kubernetes, and that's going to be things like a huge training set that needs to be managed efficiently. High performance compute requirements are also going to be demanding a ton of data at a very quick, in a very short amount of time. And you also need to make sure that as you're introducing new data into your model, that you have a means to scale the underlying infrastructure while also taking into account, some of the points that we've talked about earlier about egress charges, right? And is this highly performant data? Do I have quick access to that when I need it? Or am I going to be starving my model of these resources because I can't get it fast enough? And then last but not least is around the data availability and protection. So how do you make sure that you're not introducing sensitive data that shouldn't be going into your model or inference workloads is another challenge, right? How do you classify all of that data? So in terms of what can we do to tackle some of these challenges? We've talked about a lot of different things you need to think about, but what is out there to unleash your potential? The first is the resource requests and limits. So resource requests and limits in terms of CPU and memory are probably the most critical aspect of your potential to save money. So you can do a few things. You can make sure that you're right-sizing your containers on a daily basis. Maybe you have an automatic right-sizing solution. But that's really the first layer, so making sure things are sized correctly. You also need to make sure that you have a strategy for understanding the actual utilization of your GPUs. So you have your GPUs that are just requesting that integer number of, I need X amount of GPUs, but you have no way of doing a fraction of that without a few modifications. So that's another layer, but then you also have custom Kubernetes schedulers that can be specifically designed for AI and ML workloads. And the advantages of using a custom scheduler is it can help schedule your pods in batches, just as an example. So you can make sure you're not just spinning up a ton of infrastructure, one pod at a time. A scheduler can help make sure that you're efficiently bin packing those nodes as best as you possibly can. Okay, so I've been talking a lot about sizing your pods and setting your requests appropriately. Well, there's a few things that are out there that can kind of level the playing field in terms of what you're already doing today on Kubernetes with CPU and memory. And that concept is all around GPU fractioning. So GPU fractioning is taking the idea of essentially virtualizing these GPUs to take advantage of these different strategies. So we're going to deep dive into each of these strategies. But at a high level, time sharing is taking the idea of taking a single GPU, virtualizing that GPU, and you can say, that GPU is now worth 40 GPUs to me. And your pod requests can then follow suit and say, okay, give me X amount of that fraction. And by doing so, you can be requesting a big percent or a smaller percentage of what you were requesting previously of those same workloads. So the next layer is around multi-instance GPU or MIG. So this is physically dividing a GPU into smaller fractions, but it's a physical isolation. So it's taking the ability to create up to 7 GPUs from a single GPU, and then multi-process service GPU after that. So how exactly does that work? We'll start with time sharing GPU fractioning. It requires a couple things. Nobody said it was going to be easy to optimize your Gen AI workloads, but there's a few steps you need to take advantage of this benefit. So the first thing is you'll, in this case, you'll install the NVIDIA GPU operator into your existing cluster, and that's essentially what allows you to virtualize your GPU. So once you've virtualized it, then your subsequent pod requests or jobs in this case are all going to be able to share those, share a single GPU. And this is great for things like your CI/CD pipelines or small batch processing, interactive applications, where you don't care as much about having that same performance every single time, or you don't care about a strict isolation or guaranteed performance for every individual tasks. But this is a great strategy for being able to take advantage of saving a lot of infrastructure costs and consumption. So this is just a visualization to kind of show how all of those jobs can share that single GPU. All right, the next strategy is multi-instance GPU fractioning. So very similar idea in that you would install the NVIDIA GPU operator into your cluster. And what that allows you to do, or what MIG allows you to do, is enable multiple instances of GPU to run concurrently by partitioning it into up to seven separate GPUs. And the advantage of this is it allows a physical isolation, so you're going to get that same level of performance every time, right? So you'll get that physical isolation in terms of memory or virtualized memory of that GPU, and you can expect that same performance every single time you're running that job. So this is also a great tool to take advantage of things like not only inference workloads, but maybe training workloads or HPC workloads. So the use cases are taken to another level here, where you're really concerned around performance and being able to run things in parallel. Okay. Last but not least is the multi-process service GPU fractioning. Don't ask me to say that 10 times in a row. I don't think I can. But what MPS allows you to do is have multiple processes to share a single GPU and enabling concurrent execution of multiple tasks. So this is a little bit different in that you would be installing the CUDA multi-process service into your cluster, and that automatically and dynamically adjusts your configurations to your specific requirements. So it's another way to take advantage of applications that have those requirements where you don't need that dedicated performance, that physical isolation, but it allows for overall better GPU utilization by concurrently running multiple tasks on the same hardware. So in terms of the challenges of auto-scaling, your workloads, right? Like all of this sounds great. Why is the world not, taking advantage of all of these tools? Well, the diagrams we looked at on the previous slide make it sound quite easy, right? Like you just deploy this operator into your cluster, you start, requesting these fractions, life is good. Well, it's a little more involved than that because how do you know what your fractions are, right? You need to make sure that you have the tools in place to be monitoring real-time prior runs of those same jobs to understand what you're requesting, of a GPU versus what's actually being utilized. Once you understand that, you can start to understand your fractional requests. In terms of the cluster auto-scaling timing, this is another tricky piece because you now need to understand, or your cluster autoscaler is not going to understand these fractional components, right? The Kubernetes scheduler is going to understand how to schedule those pods correctly, but the cluster autoscaler is still going to be unaware of what these fractions mean. So what that means in practice is you would have to have your, essentially your nodes spun up in advance, and then as those pods come into your cluster, they would be scheduled. But the cluster autoscaler would be confused as to what that means and probably result in a lot more nodes being spun up than you're anticipating. So in practice, that could lead to additional costs if you're not monitoring things adequately to make sure you understand the full picture of what's being consumed. Last but not least is around resource visibility. So all of the tools that exist today on Kubernetes, or the native tools out of the box, they're not going to understand the fractionalization piece either, right? So your existing monitoring tools, are they going to understand what a fractional GPU request means, or is it going to be treating all things equal? So just another thing to think about, as you go through. Okay, so let's talk a little bit about some of the solutions that AWS and NetApp offer today. So NetApp, our goal is to make sure that we provide you the tools to tackle your AI challenges across the entire life cycle. So what exactly does that mean? That means we want to be making sure that we're supporting your workloads for things like your HPC workloads, foundation modeling, making sure that we're supporting that demand for the highest performance possible, but also making sure that we're going to support everything before that, right? So your data lake and the data preparation is really the foundation for your AI and analytics workloads. Enterprise model training, we want to make sure that we're able to help you fine-tune those areas where our intelligent data infrastructure and high performance can converge with what is already available today on NVIDIA. So finally, where we spend most of our time is around the AI inference workloads and making sure that we can not only support the compute layer, but also the storage layer to make sure that when you want to introduce new data into your environment, that it's done so in a safe way, it's highly performant, and highly available. Okay, so what exactly does that look like when we start to tie all of those solutions in? So our goal is to provide that unified experience of infrastructure, no matter where you are. So we want to meet customers wherever they're at, whether it's on-prem, you have a hybrid environment, or you're in the public cloud today. And our intelligent infrastructure services are here to provide that software layer of optimizing those workloads. So we're going to dive into more of that in just a little bit. But last but not least is around the security. So we want to make sure that not only is this a uniform experience across all of these different environments, but we want to make sure that it's adequately secured. All right, so now let's talk a little bit about how we can help automate that infrastructure optimization process. So in order to go through that, I'm going to spend a few minutes talking about our NetApp Spot Ocean tool. And our NetApp Spot Ocean tool, you can think of it like a serverless compute engine for running containers in the cloud. And the way that Ocean works is you would deploy our Ocean controller into your existing Kubernetes cluster, your EKS cluster, for example. And what that controller is responsible for doing is making sure that we're continuously optimizing your environment. So what exactly does that mean? That means we're always listening for new pods coming into your cluster. If we detect a pending pod, we say, okay, we need to scale up more infrastructure. We go back to our SaaS layer. Our SaaS layer is going to say, okay, this is how we think we should launch the infrastructure. And then we actually launch the infrastructure on a customer's behalf. So there's the intelligent scaling piece, but then there's also the optimization piece, right? So we're always looking at how can we do better? How can we make your cluster more efficient? So we run these scheduling simulations every 60 seconds in your cluster to say, can I actually make this cluster more efficient? Can I take pods from an underutilized node and put them on a different node and then terminate that underutilized node? So essentially shrinking the size of your cluster footprint. And then we also have out-of-the-box support for time-sharing GPU fractioning. So we'll dive into exactly how that works in the next slide. But we also provide a few other tools to essentially help operationalize how all of this works on Kubernetes. So the first layer, I think, is or the most important layer, maybe for your finance team, is understanding the cost of all of this, right? So when we talk about cost on Kubernetes, we no longer care about how much does this VM cost me, right? Because that VM might be supporting 10 different applications or 10 different jobs at any given time. We need to look at what do these actual microservices cost me. So that's what Ocean aims to show users is we provide that granularity of what does an actual container cost in terms of your compute, your storage, your networking, and how do you get that data back into the hands of the folks responsible. So we provide that visibility aspect. And then we also have an automated right sizing solution. So automatic right sizing with our Ocean tool essentially is taking an understanding of, okay, we see you're requesting X amount of resources, but you're actually utilizing Y, and then how can we change the actual utilization or the actual requests of what's being consumed? So we provide an automated way to right size your pods and applications, and you define the rules. So you will define things like, I still have my minimum and maximum boundaries. Don't touch this pod. This is too critical. Or maybe in my production environment, I want to add an extra buffer of CPU and memory to whatever you're telling me. And all of that is from a single pane of glass. So how exactly does all of that work with the fractionalization aspect of extended of Kubernetes? So I mentioned it a couple times, but only the CPU and memory out of the box will allow you to request that fractional piece of the infrastructure. But what you can do is you can leverage a tool from Kubernetes called extended resources. And what extended resources allows us to do is essentially understand, do this translation aspect of the fractions for you. And once we understand that fractional definition, then everything can tie together with the auto-scaling piece. So in practice, what that looks like is you would use our dedicated APIs to essentially come up with these definitions. You would say things like, okay, this instance type equals X amount of replicas for me, and this instance type is going to be Y amount of replicas, or Y amount of GPUs rather, and after that, you're good to go. So you install your NVIDIA GPU operator, and after that, it's a fully automated solution that we understand those replicas, we understand those fractions, and we can start auto-scaling and bin packing appropriately. So it's a really neat way to kind of go through that full life cycle of GPU management and time sharing from a single pane of glass. So the last aspect of optimization is around the life cycle of compute that you're consuming. So in terms of life cycle, you have a few different options. The first is your on-demand. So that is kind of the draw to the public cloud, right? You have the benefit is you only pay for what you use, right? But it's also the most expensive. Another option you have is using reservations or savings plans, which is a way to come to AWS and say, I will commit to using X amount of instances or X amount of compute per hour, and then in return, AWS will give you a discount. The challenge with that is you're committing to using those commitments, and if you have bursting or spiky applications, then it might not be the best fit because you're paying for that commitment whether you use it or not. The last layer, and as you might get or infer from the name, is Spot Ocean, and that's really our bread and butter because the last option you have is Spot Instances. So Spot Instances provide you up to a 90% discount over the on-demand cost, but what's the catch, right? Like why doesn't everyone use that? Well, Spot Instances are excess capacity from AWS, and there is capacity that's not currently being utilized. So in return, you can request these instances, get that discount, but the downside is they can be reclaimed by AWS with just a 2-minute notice. So how do you plan for that? That's what our Ocean product aims to do, is everything that we're launching for a customer is going to be using a machine learning driven algorithm that takes all of the data from our customers running on Ocean today, and that spans across every availability zone in every region to understand what is being interrupted, what types of instances are being reclaimed, what are the ongoing prices, because being a supply and demand based resource, that pricing and availability can change in real time. So we use these machine learning algorithms to only launch Spot infrastructure in availability zones and markets that we believe are going to be highly available and at the best possible price. So when you think about some of those GPU challenges, it's yet another way to save off the top of your cloud bill. Okay, so when we talk about, when we start to wrap up a bit today, I want everyone to leave here today with the mindset of if you're on the DevOps team, our goal is to make sure that no DevOps engineer is left behind. So, in order to do that, we want you to understand that these GPU instances are very expensive, but we also want to make sure that you understand and have the tooling available that if your workloads are not consuming an entire GPU, you have the automation in place to actually right-size your applications, and you have the ability to only request that fractional piece of your of a GPU to save money. And of course, our solutions are here to automatically help with that piece out of the box and utilize those time-sharing capabilities to optimize your infrastructure utilization, scaling, and cost efficiency. And where are we going with that? Or where are we going next? What is the future of AI with Spot Ocean? Well, I I think it's safe to say we're not done yet, but our goal is to make sure that the fractional piece of GPUs is a seamless experience for your DevOps team to manage, and we're going to continue building mechanisms to make that even easier, right? So we don't want you to have to spend a lot of time trying to understand all of this fractionalization piece, installing all these components. We want to make that as simple as possible for all of your different workloads. We want to make sure that these scarce GPU workloads are no longer a concern. Our goal with Ocean, or any type of scaling issue with Ocean, we consider a catastrophic failure. So our goal is to make sure that you always have the infrastructure that you need at the best possible cost and the highest availability. And of course, in order to do that, we need to make sure that our models, right, that is supporting your infrastructure are constantly serving the best possible data, and we're able to serve customers with that reliable infrastructure. And then in order to solve for that last piece around complexity, our goal is to make sure that your DevOps team has a seamless experience to tackle all of this together. Okay, so that wraps up our session today. I'll be hanging around